nanoHUB.org.
Online simulation and more for nanotechnology.
So I'm going to be talking about the effect of stochasticity in systems that have tightly integrated dynamical as well as event-driven evolution. So a CPS modeled by a discrete time stochastic hybrid system. Now, when I think about resilience, some of the issues that came up to me were not only the need to provide built-in robustness, so to anticipate failures given known dynamics, known stochasticity, and anticipated bad states. So the problem is simply how to identify when you might end up inadvertently in one of these bad states. But also runtime detection as well as anticipation of faults. So there's a certain amount that you can do offline, but more challenging is identifying problems as they happen in real time that you may not have thought to identify earlier or could not have been able to identify earlier with some of these a priori methods. And then lastly, another challenge is that of recovery from error. So if you do have some sort of fault, then what are the possible states that you could get to recover to some degree, and how quickly can you do it? These are huge challenges that are beyond state of the art. But I do think that stochastic prediction and verification are core technologies that are necessary for all of them. Some of the predominant challenges in this area have to do with how we can handle stochasticity in a way that is amenable to formal guarantees. There's usually a trade-off between accuracy and efficiency. And so the only way we can get better and better results is by increasing our computational cost, which is obviously counter to trying to be able to do these things for very large systems or for very quick response. The approximations that we use, we need to be able to have rigorous assurances as to the implications of the approximations, not just general convergence, but a lot of times we need convergence in a certain direction. We need to know that we have an under-approximation for the problem of safety, for instance. Controller synthesis, always a challenge. Different assumptions on what kind of controllers we have access to can again change our computational efficiency for some of these algorithms, but enlarging the scope of controllers that we can conceive of can increase the scope of what is considered to be safe and therefore what is to be resilient. And then lastly, meaningful metrics. Finding the appropriate ways to describe resilience beyond some of the metrics that are currently used is probably a very, very important aspect, particularly as we are involving humans in this process as well. So some of the applications that my group has been thinking about over the past few years, flight management systems in aircraft, some problems in target capture and stochastic target avoidance in UAVs, automated anesthesia delivery, as well as spacecraft rendezvous and docking. Okay, so the prediction problem. Broadly speaking, the problem is that we have a given initial condition, so we know where we're starting from, and we just want to figure out what's the probability distribution function of our state that is driven by some potentially nonlinear dynamical system that could even be hybrid, meaning that there's events as well as physical dynamics driving the system at some future time. And while this sounds like a very simple and straightforward problem, when we have nonlinear dynamics, when we have non-Gaussian disturbances, it's not so straightforward. We want to be able to do this in a very fast and efficient manner. So how can we do this without grids, without recursion, and without sampling? So there are some methods. We've been looking at exploiting characteristic functions. And so this is a method that sped things up quite a bit, but still requires a sampling for this general nonlinear form. If we're willing to make some assumptions about the types of systems that we can handle, linear dynamics, about the types of controllers, open loop versus closed loop, then we can actually take advantage of some properties, mathematical properties, to speed up some of these calculations. So we've been doing work on characteristic functions, so essentially a Fourier transform of our probability distribution functions. And the reason that we've been interested in this is that it allows us to obtain a closed form solution when we have linear time invariant dynamical systems underlying the evolution of this probability distribution function. So the general idea is that you can simply take this expected value, you can get your characteristic function here, and it's possible to then take an inverse Fourier transform to get back your PDF. Usually. So where this is useful is if you have a linear time dynamical system, we have a closed form expression. We know what our state is going to be at some arbitrary future time. And if we can characterize the disturbance that is influencing the evolution of the system, if we know it's PDF, we can compute the Fourier transform, figure out, therefore, what the characteristic function is of this random vector that represents a state variable, and then take the inverse Fourier transform when it exists, and we get the PDF. So this is without sampling, this is without gridding, and this is an efficient method. We've been able to apply this to non-Gaussian distributions. An example is shown here, along with the Monte Carlo simulation of what the, quote, true answer would be. So this widget is a promising start to being able to have these tools that are a necessary element for many problems in resilience. The other tool that I want to mention briefly is that of stochastic verification. So we've been using efficient predictions to then enable questions about verification. So we're trying to answer the question, if you're given initial state, does there exist a control that assures that your state satisfies whatever constraints that can be represented as a function of the state space are satisfied with at least a desired likelihood? And these constraints, there's a variety of niches in this problem, viability, where you're trying to stay within a good set, or reachability, where you're trying to reach a target or start from a known position and then see where you end up. This idea of having these time-varying target tubes is actually a framework posed by Bartsekos in the 70s that encompasses all of these. The second question is, rather than looking at a specific initial condition, trying to identify all sets of initial conditions, the largest set, ideally, for which there exists a control law that satisfies this safety, the ability to stay within those constraint sets probabilistically. And then second, with what control law? So we want to do both, ideally. We want to figure out, if we know what the dynamics are going to do, given the stochastic influence, how can we anticipate where we should be to avoid problems, and what controller should we use in order to assure that we can maintain at least that level of assurance? Now, the problem is a very difficult problem to solve. It's based in a dynamic programming solution. And so solving this in a scalable manner with these guarantees of under-approximations is important. If we have an over-approximation, then it doesn't give us that guarantee of safety anymore. So the under-approximation is critical. And again, we want to be able to do this without grids, without recursion. Sampling is sometimes a good thing, so that's fine. But conservatism is really one of the main challenges. So this is the mathematical formulation of this problem. We're trying to maximize the expected value of a product of indicator functions. And these indicator functions give you a 1 if you satisfy the constraint, so if you're in the set Ti, and a 0 otherwise. So you get a bunch of 1s multiplied together if everything is good. And if one of them is violated, then your cost function goes to 0. So you're trying to keep the cost function as high as possible. And that's your likelihood of safety, your probabilistic value of the reach avoid probability. So we know mathematically that the solution to this problem can be written in terms of a dynamic program, which of course we don't want to have to solve. And so for a specific initial condition, we would be basically evaluating this cost function, this optimal cost function, at a specific initial condition. So in the original dynamic programming solution, we get the answers to both problems as well as the control law all at the same time. We know that the optimal control policy that results from this is a Markov policy, and it's also feedback-based. But this is clearly not computable. Now, the nice thing about this is because it is amenable to a discrete time stochastic hybrid system formulation, it's quite generic. So we can have this framework, the discrete time stochastic hybrid system, actually boils down to a Markov process. And so it ends up being fairly generic. We formally specify a transition function for the evolution of the continuous state, and then an update function for the evolution of the discrete elements, the modes. So my lab group has been looking at how we can exploit mathematical properties associated with specific cases that take advantage of structure. And when we have linear dynamics, when we know that our target sets that we want to stay within, as well as the input set, are compact and convex, and when we know our probability distribution function has a log concave form, then we can actually pose this as an optimization problem that is log concave. So this is great. We have something that is tractable and efficient. This is a conversion of the expected value of the product of indicator functions. The effect of the indicator function is essentially you're multiplying you're integrating the probability distribution function over each of the target sets in time. So here is the distribution of the state, and we're just taking the integral over time, over the sets of interest, subject to the evolution of the state according to the dynamics, and its distribution will be driven by that of the random vector that's the disturbance. And this is basically saying that our input is going to be bounded. Now, the assumptions that we've made, in addition to this, is that our control law is open loop. So we're not allowing for a feedback-based control, which means that our result is going to be conservative. We have seen in practice, though, that the conservativeness is not excessive. It seems to be a useful abstraction, a useful simplification. We have also been able to prove things about the reach avoid sets that we end up with. We know that under these circumstances, we'll end up with something that's convex and compact, which means that we have a whole set of new possibilities open to us in terms of algorithms to compute not only the probability measure, the likelihood of safety, but also the super level sets for which we know that safety is guaranteed with at least the desired likelihood. So these are some of the computational results that we've had. This is up to a 20-dimensional system, so dimension of the continuous state, which tends to be the bottleneck because of the explosion in the state space dimension. With a couple of methods, we've also been able to, well, let me back up. So this guy, for this Fourier transform method with optimization, is shown in this black line. So it's fairly flat as dimension increases as compared to dynamic programming. We've also implemented chance-constrained optimization approaches that take advantage of this fact as well, and that's shown here. We've also most recently looked at scenario-based approaches, which don't rely upon the characteristic function, but are computationally efficient as well. This is showing how we can use this kind of result to identify a likelihood of safety in the state space for a problem of spacecraft rendezvous and docking. So when two when two satellites are getting close and they want to do this maneuver, they have to stay within a line of sight cone so that they can sense where the other satellite is. And that's described here in the relative coordinate frame. So the question is, where can this maneuver be accomplished safely? How can you stay within the line of sight cone and get to the place to dock within the allotted time frame? This is a trajectory that was generated with this approach using the optimization. We were able to also solve for this, to solve for the reachable set. These tools are available on my lab's GitHub website. So with this tool for prediction, we can then treat calculation of the reach likelihood as essentially a query. We've been able to formulate an anytime algorithm to solve for the stochastic reachable set by first finding a feasible point within the desired level of safety that we want. So this is a picture of our likelihood of safety. If we find a point in that region, then we simply start identifying directions that we're going to shoot rays in to find the point that maximizes our likelihood in this direction. So essentially what we end up finding is a point that's going to intersect with the stochastic reachable set. It's an anytime algorithm because we know that the resulting shape is going to be compact and convex. So if we have more directions, we'll get a better answer. But we have fewer if we have fewer directions, then we know that our result, the shape that is the convex hull, is still going to be an under-approximation and therefore meets all of our criteria for safety. Now we've been applying this to a variety of applications. This is a motion planning one that we did in collaboration with Directorates at University of Washington. So now that we have this ability to make these fast predictions, we can, with an MPC type of framework, account for the likelihood of where other dynamic obstacles in the environment are going to be, and then plan a trajectory using successive convexification, because we have these properties of convexity and compactness that we know now pertains to our reachable sets. We've also been looking at problems of target capture as well, where we're trying to get close to something that is moving in a stochastic and dynamic fashion. So with this basis, there are many new avenues open to us. We have recently been looking at how to extend the scope of control laws that we're examining to allow for feedback-based control, which will give us a broader region of the state space that is safe. We're looking at extensions beyond LTI. We know that it's possible to model some linear parameter varying systems as well as linear time varying systems, which is nice because then we can model things like the Dubin's vehicle, which is going to be very relevant for a lot of these motion planning types of problems with this kind of framework. I think a more challenging problem is going to be how to handle the presumption that we know the distribution of the uncertainty of the disturbance input accurately. And so looking at how to characterize and accommodate uncertainty in the distribution is going to be important. And more long term, we want to do things, we have certain ideas about what is bad. For instance, states outside of an aircraft flight envelope. Those are bad. But there might also be we need to be able to do this on the fly. We need to be able to come up with alternative ways of identifying things that don't rely on enumerating faults. Integration and adaptation with data-driven methods. I think this is also going to be really critical for looking at autonomous systems that have these learned elements, or also for human-in-the-loop systems where we're relying heavily on the fact that we have a model we know, and that may not always be a good assumption. So how do we handle those cases and exploit the bounds and properties that we've been able to derive for these cases? And then additionally, looking at how this information can be used to design systems that have soft fails, right? So that if there is a failure, the consequences won't be so drastic. All right, I'd be happy to take any questions.
Are there any questions? Okay.
Really interesting, Meeko. So it seems like one challenge in going to the nonlinear setting might be sort of the standard chaos argument, right? Yeah, these nonlinear dynamical systems, small changes in initial conditions could lead to wildly divergent trajectories. So I wonder, do you anticipate when you go to beyond the LTI systems that there are certain classes of nonlinear systems that may not be amenable to this kind of analysis?
It might be better to pose which classes of nonlinear systems might be amenable, because I'm sure that there's plenty of classes which would cause huge problems. Nonlinear is just such a huge term. I think that where some of these techniques might be extendable are ones that are amenable to some sort of approximations or bounds, right? Because if it looks linear in a certain region, then we can use that same idea of taking advantage of structure and assuring that we have properties so that we don't have to compute everywhere, just at certain points, and we know we still get a good answer. We've been able to do the convolution method for propagating uncertainty works for nonlinear. It's just that you're doing this at every single time step. So it's accurate. It's just takes a long time.
You didn't speak about it, but you mentioned that you do some stuff with closed loop anesthesia.
Yes.
To which point I would ask, assuming a system is resilient without including the human in the loop, in the medical domain would be a little presumptive. How could your techniques be extended to provide feedback to the human operator to improve the resilience?
So I think there's two problems. One is coming up with effective models of how humans behave, because if you treat them as a source of uncertainty, that could have a dramatic effect on your system safety. And then the issue of interface design. My lab's been looking at problems in interface design for a little bit, primarily from an observability point of view, where we're posing whether or not the user has adequate information to be able to reconstruct the true state of the system. I think that in the long term, integrating some of these methods with ideas about observability would be important. In the short term, I'm not sure how to go about doing that. There's a number of big challenges there.
Are there any more questions? So I have one question. You mentioned about uncertainty in the distribution and also data-driven methods.
Mm-hmm.
Can you argument more about what kind of guarantees you can provide when you have, when you don't know the distribution and your dynamics of your systems, and how can you apply?
So we've been looking into some methods recently that basically evaluate the distance between observations. Mm-hmm. So it relies on sampling to characterize your environment. And we believe that the accuracy of our stochastic reachability result will be as accurate as your samples will be at that point. So that's a promising start, I think. But I think we can do more there, because currently those methods don't take into account any knowledge of the dynamics. They presume that it's a completely black box, which I think is a bit much. Mm-hmm. Especially given that for the problems that we're looking at, they're physical systems where there is a human in the loop, or there's some uncertainty in how the physical systems are operating. So I think that's a place to begin. And some of these methods are structured. Some of them are amenable to convex optimization. And so I think that'll be our saving grace.
Okay.
The data uncertainty, I'm not sure. There is somebody at USC In-Sun Yang, who is working on some of those problems, but he's not looking at it from a computational efficiency perspective. He has some theoretical frameworks to start that.
Okay.
Yeah.
Thank you.